Okay, this is Honors Physics, Chapter 17, Part 2, and the second half of Part 2. We're going to talk about convex mirrors, and we're going to talk about some equations and doing a little bit of math. The shout out goes out to Celeste, just because I can't ever remember giving Celeste a shout out. So anyway, so she gets a shout out. But anyways, so let's go back and talk about mirrors. Again, if it's caved in, it's concave. So if you look at the inside of the mirror of a shiny spoon, you're looking at a concave mirror. If you turn it over, then you have that pooched out part, and so that's convex, the opposite of concave. And when you look at it, everything seems upright, but the image seems smaller. And that's what we're going to find when we look at a convex mirror. So if we look at this idea here, we have our object on the outside of the convex mirror. Convex is over here. So then the center would be someplace over in this region. The focal point is halfway between the center and the mirror, so the focal point is here. And once again, we're going to be looking at these rays. If we look at the rays in relationship to the principal axis, we find that the rays are going to do a couple of things. Once again, we have to look at this focal point and keep in mind that the center point is behind the mirror. And so we have F, which is the focal point, and DI, which was where the image shows up, are going to be negative numbers because they're behind the mirror. So that's all the negative means, is it's just on the other side of the mirror. If we look at our ray diagram, and this is going to be important, we have a couple of rays that we can look at. I'm going to walk through them and then we'll see what the slides say. We have ray 1 that comes in parallel to the primary axis. If you draw a line from the focal point to where the ray hits the mirror, that's where the ray is going to reflect off at. On the other hand, if you have a ray that comes in aiming towards the focal point and crosses the mirror, when it crosses the mirror, it reflects out once parallel to the primary axis. So that's this whole thing. If it comes in parallel, it's going to reflect off at an angle that goes through the focal point. If it comes in going through the focal point, it reflects off parallel. So we just need to be able to draw our rays. So the figure uses two rays, but remember there's an infinite number of rays. Ray 1 approaches parallel to the principal axis. The reflected ray, if you draw a line of sight from F through where the ray hit the mirror, that's where the ray is going off to. We're not going to see that one, it's going to go away. Ray 2 is going as if it would pass through F. Again, it's going to then reflect back parallel to the principal axis. They're going to diverge, which means that you're not going to see an image on this side of the mirror. There's no point where the rays intersect. Where they do intersect, however, is on the other side of the mirror at this point right here, L1. So that's where the image is going to, or I1, that's where the image is going to be. So we have an image produced, is going to be a virtual image. Remember, there's no real image produced because real images are on the same side of the mirror as you, virtual images are on the other side of the mirror. It's going to be right side up, and it's going to be smaller, always, always, always. You experience this with your car. Objects in the mirror are closer than they appear because they're smaller than they appear. Okay, in that mirror, that allows it to give you information or visual image of a wider thing. If you have a lot of smaller things, you could fit more smaller things onto the mirror. So now you're basically seeing a wider range. That's the whole point of that. They do that on the passenger side mirror because you just want to have that information that there's stuff out there. The driver's side mirror, they're not going to do that because that would really mess you up if you're relying on that too heavily. Spherical mirrors can be used to develop a simple equation, and we're going to use this paraxial ray approximation. In other words, we're only going to be able to use the rays that are coming in fairly close to the principal axis. Once again, we get distortion if we get too far away from the principal axis. What we're going to use then is we're going to use focal length F. We're going to use the object position, which is D for the object. Also seeing it as X for the object is the distance that D is away. We have the image position, which is DI, and again the distance would be XI for our spherical mirror. And so for spherical mirrors, and actually this applies to whether it's convex or concave, believe it or not, we'll see how this works out, is that the reciprocal of the focal length, 1 over f, is going to be equal to the total of 1 over xi, 1 over xo. So the distance to the image plus the distance to the object is going to be equal to or 1 over the distance to the x, 1 over the distance to the object is going to be 1 over the focal length. We have to use reciprocals. Other than that, it's a pretty straightforward formula. Doesn't predict the aberration because it uses paraxial rays, so just keep that in mind. Ray again is coming from all different directions, diverging, and all the lights close or to the parallel. If we use a relatively small diameter mirror, then basically we minimize this what's called spherical aberration. Magnification. When we talk about magnification, these mirrors, whether it's a convex or concave mirror, is going to change the size of the image, and we use magnification is basically a ratio of taking the height of the image divided by the height of the object. If the image is smaller than the object, we get a magnification that's a fraction, like 1 over 2. In other words, we're cutting the size in half. If the image is larger than the object, 2 over 1, then we're doubling the size of the image. If they're the same size, magnification is 1, which means that there is no change in the size. Magnification of 1 is basically everything is normal. And we can either get that from the height of the objects or from the distance that the objects are from the mirror. Both the image and the object are from the mirror. So we can use these ratios. So where do we come up with these numbers? Well, we're going to see this in a few minutes. Now, keep in mind, magnification is negative, which means that we have an inverted image. So when we have a negative magnification, we have an inverted image. That's all that means. So don't let that negative throw you off. All right? Now, when we're calculating the image, there's some things that we have to take into account. Are we behind the center point of the arc? If we are, then the absolute value of the magnification of the real image is less than 1. In other words, we're going to get a smaller image. This means that the image is smaller than the object, and the object is placed between the center point and the focal point. The absolute value of the magnification of the real image is greater than 1. In other words, the image is going to be larger. Okay, so we're going to take that into account when we look at these images. By the way, the focal point for a convex mirror is on the other side of the mirror. There's no way you can get between the center point and the focal point because both the center point and the focal point are on the opposite side of the mirror. That means that you can never get a larger image from a convex mirror. The only concave mirrors will give you a larger image. So we're going to look at a concave mirror. Radius of 20. In other words, C is 20 from the mirror. We're going to look at an image that's 2 centimeters tall, and the object is 30 centimeters from the mirror. So in other words, the object is further away than the center point, than C, which is, again, the radius of the circle. And we want to figure out where the image is and what the image height is going to be. So we're going to start with a ray diagram. Now, you're going to have to draw these ray diagrams, so let me walk you through drawing a ray diagram. Let's first of all start by drawing your curved mirror. This is going to be a concave mirror. We're going to draw the principal axis. We're going to establish where C is, the center point of our curve is. The focal point is halfway between C and the mirror. And we're going to put an object out here. This object is going to be further away than the center point. Remember, x0 is the distance it is. The xo is the height of the object. Now, if we put some rays in here, we have a ray that's coming in parallel to this principal axis. It's going to hit the mirror, it's going to reflect off, and it's going to go pass through the focal point. So you can draw this ray in, just if it's drawing in parallel, wherever it hits the mirror, draw it through the focal point, draw your ray. We add a second ray. The second ray you're going to draw is going to go through the focal point. extend it through the focal point till it hits the mirror, and if it hits the mirror and went through the focal point, it's going to come out parallel to the primary axis. Okay, so we got these two rays drawn. Where they intersect right here is going to be where the tip of the image is. So we're going to have the tip, the top of it pointing down, and the image is going to show up right here. We're going to be able to figure out what HI is and what XI is based on the focal point and the distance from the mirror and the size of the image. So again, we're back to this. So that's how you draw these things. Draw the diagram first, please. Draw the diagram. It's going to tell you that you have an inverted image. It's going to tell you that you have an image that's smaller. That way when you do the math and you do the other stuff, if you don't get that, you know that you did something wrong and you could go back and solve your work. So what are our unknowns in this case? We have a height that's 2 centimeters. We have an XO, the distance from the mirror is 30 centimeters. And R, remember R is basically the distance to the center of the circle. Why is that important? Because half of that will give us the focal point, and we need F. We're going to try to figure out what XI is, what XHI is. We're also going to figure out what the magnification is. So if we're going to solve, first of all, this is the easy one. The focal point is half of the radius of the curve. So if we know what the radius is divided by 2, we start out with 20 centimeters from the center of the circle to the mirror. So the focal point is half that, or 10 centimeters away. Now, we have our mirror equation. And again, this equation works whether we're dealing with regardless of the type of mirror that we're dealing with. And we have 1 over F is equal to 1 over I, XI, plus 1 over XO, the distance to the image, the distance to the object. They've manipulated it here. I'm going to show you how to calculate it without doing this manipulation. If we have the formula here, we simply substitute in. We know that F is 10, so we put a 10 in. We're solving for XI, so leave that alone. We know that XO is 30. Subtract 1 over 30 from both sides. You get 1 over 10 minus 1 over 30 is 1 over XI. Common denominator is 30, so convert the first fraction to something with a denominator of 30. 3 over 30 is minus 1 over 30 is 1 over XI. So 3 minus 1 is 2. 2 over 30 is XI. Cross multiply. 2 over X is equal to 30, and divide by 2, and you get XI is equal to 15. 15 centimeters then. So now we have a good, we have 15 centimeters. They solved it by manipulating it first and substituting in. They also get 15 centimeters. Real image in front of the mirror. Okay, that's what a real image means. It's in front of the mirror. It's not behind the mirror. Now, magnification. Magnification is HI over HO, or negative HI over negative XI over XO. Again, we're going to solve for XI so we could figure out what the height of the image is. So they manipulate it first. I'm going to show you how to not manipulate it and just substitute in. So XI is what we're solving for. HO is the XI we figured out was 15, so the formula tells us this is a negative 15 over 30, which is XO. Multiply both sides by 2, you get a negative 30 over 30, which is equal to a negative 1. So you have HI, the height of HI is going to be, instead of 2 centimeters, it's going to be 1 centimeter. Okay, the negative tells us it's inverted. In other words, it's below the primary axis. If we wanted to solve for the magnification, again, we could either use either one of these two formulas, either a negative 1 over 2 or a negative a half, or negative XI over XO, negative 15 over 30. Both ways it gives us a negative a half. The half tells us we're cutting the image in half. The negative tells us it's going to be an inverted image. Now they went ahead and manipulated the equation, solved it, and once again they came up with a negative 1, an inverted image, smaller image. So the positions of the centimeters, that's good. Position is negative if we have a negative height, basically it's below the parallel axis, so that's good. Looks like everything lines up. Now, a couple of things to remember. If we have a plane mirror that's not curved, since the focal point is at infinity, essentially the only M you're ever going to get is going to be the same size. There's no magnification. The M is always going to be 1. The image is going to be on the other side of the mirror, which is going to be a virtual image. On the other hand, if you have a convex, let's drop to the bottom. We have a convex. Since the focal point is on the other side of the mirror, the only thing that can possibly happen for magnification is it has to get smaller, and you're only ever going to have a virtual image. The concave is the one that's a little trickier. You're going to have a positive focal point, someplace between the center and between the center of the circle and the mirror. If the object is further away than the center, in other words, XO is greater than R, you're going to have a reduced inverted image, and it's going to be a real image. It's going to be on the same side of the mirror as you. If it's between R and the focal point, you're going to have an enlarged inverted image. Again, it's going to be a real image. The image is on the same side as you are. But if you get the object closer to the mirror than the focal point, so between F and the mirror, you're going to get an enlarged virtual image on the other side of the mirror. It's going to be right side up. So virtual images are always behind the mirror, which means that the image is negative. The position is negative, not the other number. The absolute value of the magnification is between 0 and 1. The image is smaller. The negative magnification, when you have a negative magnification, it means that the image is inverted. So a single plane mirror and a convex mirror only produce virtual images, whereas a concave mirror can produce either real or virtual images. Plane mirrors give simple reflection. Convex mirrors expand the field of view. Concave mirrors can act as a magnifier if the object is closer than the focal point. So that's it.